So I'm going to ask you to stop the video right now and have a go at this exercise. You've got this molecular formula, C4H8O2, and you've got a proton NMR spectrum. What structure corresponds to these, could correspond to this proton NMR spectrum? In brackets, you have numbers, and those numbers equate to the integrator trace. So it tells you how many hydrogens you have in that particular environment. So you've got the splitting because you can look at the structure of the spectrum, and in brackets in red with red numbers you have how many hydrogens are actually in that particular environment. So stop the video now, please. So I hope to stop the video and have a go at the exercise. Let's see what I would do. The first thing I notice is the integrations. It tells me how many hydrogens I've got in total. And I see that the ratio of the integrals of the integrator trace is 2 to 3 to 3. And that actually corresponds to 8 hydrogens. So in those signals I can see all the hydrogens, the 8 hydrogens, and these integrator traces, these ratios corresponds actually to real number of hydrogens. So here this multiplet corresponds to a CH2. Here this singlet corresponds to a CH3 group, and this triplet here corresponds to a CH3 group. The next step is look at the multiplicity of those peaks at the splitting. Let's start with the peak at 2 ppms. It's a singlet. That means that n plus 1 equals 1, which means that n needs to be 0. What does it mean? That means that this methyl group, these hydrogens that are in this methyl group, are next to a carbon or an atom that does not have any hydrogens attached to it. So I find that in mind and I think, okay, well, I've got a CH3 in my structure that is attached to something, potentially a carbon, but there are no hydrogens in that neighboring carbon. And that's where I have a singlet, no multiplicity. Then I look at this multiplet. Okay, it says 4 signals, so it's a quadruplet, and I think, well, n plus 1 equals 4. That means that n needs to be 3. What does it mean? Well, that tells me that I've got this CH2 is next to a carbon with 3 hydrogens. So this CH2 is next to a CH3, a carbon with 3 hydrogens. And if I look at this peak here, a bit over 1 ppm, I notice there is a triplet, so n plus 1 equals 3. That means that n is 2. What does it tell me? It tells me that this CH3 is, these hydrogens in this CH3, in this methyl group, are next to a carbon that has 2 hydrogens. And that's quite a typical pattern. You see the quadruplet and the triplet, and that means that you have a CH2-CH3 structure in your compound. And now I just need to know how to put it together and how to combine it. At the moment, I have accounted for 3 of the carbons, all the hydrogens, and I still have 1 carbon left and the 2 oxygens. And then I need to think how I might be able to put this together, and that's when I need to look at the chemical shift and compare them with a table. And if you look at a table of chemical shifts, it will show that these peak around 1 ppms, I think it suggests between 1 and 2 ppms, are typical of hydrogens that have a carbonyl group and a nearby carbonyl group. And that's where they appear around this point, this chemical shift. So my suggestion would be that here I've got a carbonyl group that would account for my 4th carbon and 1 of the oxygens. And then it is likely that the other oxygen will be here in the form of a, in the form of an ester. And if you look at the previous slide in which there were some chemical shift for proton NMR, it suggested that hydrogens in a carbon that is also attached to an oxygen would appear, I think, between 2 and 4 ppms. So so it would it seems reasonable that it would be this one 2 and 4.5 or something like that. So that would be a good candidate for this peak here. So this is how propose the structure of this compound will look like. That fits quite nicely the spectrum I've been giving. Just a quick word about the hydrogen attached to an oxygen in a hydroxyl group. It appears as a singlet. It's not affected. The oxygen does not allow this splitting, this influence of the hydrogen from neighboring carbon atoms. So it appears as a singlet. It can be complicated to identify because its position varies depending on the conditions the spectrum has been recorded. For example, there is typically an exchange of that hydrogen from the hydroxyl group with water in the solvent, in which the NMR is recorded. It could be even if the solvent is not water, but there will be a small amount of water in any solvent just because it's kept in sort of open conditions, and that will affect the position of that peak. So to identify the peak corresponding to the hydroxyl group, it's very common to add a few drops of deuterated water. There is an exchange, an acid-base exchange, between the hydrogen of the hydroxyl group and the deuterium of the water, of the D2O, and that will mean that peak will disappear. So if you notice the spectrum at the bottom, you have this peak around 1.8 ppms. It's relatively broad and it's a singlet, and when adding a few drops of deuterated water, it disappears, and that is a very clear indication that that peak corresponds to the hydroxyl group in the structure of the molecule. NMR is widely used in many fields in chemistry and outside chemistry, agriculture, food industry, the study of polymers, in the health, in molecular imaging, in the health, you see it by the use of MRI scans in hospitals. It gives you great structural information. It's a non-destructive technique, so there's nothing happens when the sample is exposed to magnetic radiation, and and peak size is correlated to the concentration, so it can be used for not only for qualitative studies but also quantitative ones. You can quantify the amount of the compound you have, not only what you have. As a mild disadvantages, the equipment is expensive. There are hundreds of thousands of pounds can be spent in buying and maintaining an NMR. And depending on how complicated the structure is, there's a great possibility for user error. So it does need to, it does need an experienced scientist interpreting NMR, because they can get very complicated when you have a high number of carbons or hydrogens, depending on if you're looking at carbon or proton NMR in the structure. So this is all from me. I hope this was useful, and I hope you have learned more about NMR spectroscopy. As usual, if you have any questions, please let me know. So thank you for watching.